We're going to be talking about sort of some kinetics basics on this video, just the beginning part of it, and then also collision theory, talking about why things happen and when they happen. So the first thing you need to know is that kinetics is about the study of the rate of a reaction. So the key word there is rate. Rate for us in chemistry is either how fast or how slow reaction is happening. So it's really about the speed of the reaction. That's the most important thing that we're talking about in this unit, is just how fast things are happening. Is it a slow rate? Is it a fast rate? And then also what things go into changing the rate. So that sort of the thing that can sort of determines how fast and how slow a reaction happens is called collision theory. So collision theory says that sort of three things have to happen in order for a reaction to take place. Number one, um, two atoms or molecules have to collide. And it's always two things. It's never three things colliding together at the same time. It is only two things ever collide at one point in time. You'll see this in mechanisms. The mechanisms are always um, bimolecular, so it's always two things colliding. It's never three things at the same time. Um, if you have to have three different reactants, it's always going to go stepwise, and that's why we have mechanisms. Number two, it has to have the proper orientation. If things don't collide with the proper orientation, so let's say they have to collide like this, right? In order to make a reaction happen, they have to collide like this. If it collides sideways like this, it won't happen. So they have to collide with the proper orientation in order to make the reaction happen. And then the third thing is they have to collide with um, the activation energy. That's E sub A or greater. So we have to have enough energy or greater than the activation energy when they collide. If they don't have enough energy to make the products, it's just going to bounce off, and then they're going to continue colliding until they do have enough energy. So any of the things that we change, um, temperature, the amount of substance, the concentration, surface area, any of these things is going to affect one of these three um, major things that go into um, collision theory. So let's talk about the things that can change. So some things we can change. First, concentration. Concentration definitely can affect the rate of a reaction. If you change the concentration, it will typically change the rate. Typically, it's more concentration means greater rate. So essentially, that's more stuff equals greater rate. Now, if you have more stuff around, you're going to have more collisions. If you have more collisions, you are going to speed up the reaction. So, in general, if you have more stuff, the rate's going to be greater. It's not always true. If you have what is called a zeroth order reaction, the concentration is independent of the rate. It doesn't affect it at all. Those are relatively rare, though, and you wouldn't really know if you're given a question. It's not going to say, you know, it's zeroth order. It's going to be a little less tricky than that. And if they don't tell you, you can kind of assume that the concentration will affect the rate. Another thing that we can change is the temperature. These are probably the ones that are most commonly changed, is concentration and temperature. Um, temperature, if Remember that temperature, our definition of temperature is the average kinetic energy. Um, average kinetic energy. So if you change the temperature, increase the temperature, for instance, if you increase the temperature, you are going to be increasing the average kinetic energy. If you increase the average kinetic energy, more molecules will collide with the activation energy. So if we increase temperature, increase temp, that's going to equal a greater rate. These are probably the most common ones that are um, used, and it's to change the rate of a reaction. Um, some other ones that we can add a catalyst. So adding the catalyst, it will increase the rate. I mean, that's the whole point of a catalyst. A catalyst increase rate. That's their job. So if we add a catalyst, we increase the rate. Now, most of the time, what the catalyst does is it changes the orientation. That's most of it. Essentially, what it does is it holds one molecule at a certain angle, and then it allows the other one um, to approach and hit it with the proper orientation. That's what most of them do, especially enzymes in the body. Um, they definitely change the orientation um, more than anything else. Another one is surface area. Now, surface area is kind of weird. Um, in order to increase the rate, we need to increase the surface area of whatever we're talking about. Now, surface area really only applies to solids, um, because we can easily change the surface area of a solid. Um, so if we have greater surface area, that's going to increase the rate. So in general, if you have like a large chunk of metal and you throw that into a solution, compared to if you were to take that metal and grind it into a fine powder, the fine powder has much greater surface area. Small particles have a greater surface area than really, really large particles. So typically we want to have small particles in order to increase the rate. And the last one's state of matter. Now I will say state of matter doesn't come up very often. Essentially, we want things that can move around more, so that would be gases. So gases have a greater rate than liquids, which have a greater rate than solids. So if you can have it in a liquid form versus a solid form, that's better. If you can have it in an aqueous form versus a solid form, that's better. In general, if you have something that can move around more, you're going to have more collisions, which means you're going to have a greater rate. The second thing I want to talk about is just the basics of rate laws. So what a rate law is um, it's a term. It is an equation that shows what affects the rate and then to what degree does it affect the rate. So a rate law is going to look like this. We'll do rate is equal to k times the concentration of something to some power times the concentration of another thing to another power. So let's say this is our reaction. A plus 2B yields 3C. So that's a reaction. The only thing that ever shows up in rate laws are reactants and a catalyst. Um, Intermediates don't show up. Products never show up. Those things never show up. Rate, because these are brackets, rate is always going to be measured in molarity over some unit of time. So molarity over some unit of time, we'll call that T down below. Now, this term right here, this K, this is called the rate constant. Rate constants are temperature dependent. If you change the temperature of a reaction, the rate constant will be different. So they are temperature dependent, and there are also their units change. And the only reason why it has units is to make the other units cancel. That's the only reason why. Now, these are the reactants we have in this reaction. And then there are two powers, right? So this is power of x and power of y. The cool thing about rate laws is that it all comes from experimental data. You can't look at this reaction at the top here and say this is going to be a 1 and that's going to be a 2. You can't do that. You have to have other data to tell you what the rate law is and what they call rate orders. 0 with first and second order. Um, you can't just look at a reaction. You have to have some um, some data given to you, whether or not it is like doing it by initial rates, which is like those big tables with multiple trials, or if it's you're given time versus concentration data, or it could be even by half-life. Um, but you can't just look at a reaction and determine what the rate law is.